In this video, we'll discuss potential energy in general, and then at the end of the video, we'll discuss the potential energy associated with the gravitational force specifically. In a later video, we'll also discuss the potential energy associated with the elastic force. Conceptually, we can think of potential energy as energy that is stored in a system and can be converted into some other form of energy like kinetic energy in its entirety. This is only possible with a few types of energy, specifically those associated with conservative forces. So before we go any further, let me explain what conservative and non-conservative forces are. First, all forces can be categorized as either conservative or non-conservative. Let's start with conservative forces. There are two important characteristics that define a conservative force. First, when a conservative force does negative work and removes energy from a system, that energy is stored so that the same conservative force can then do positive work to the system and return all of the energy that it previously removed. An example is the force of gravity. Say a ball is thrown up into the air. Let's assume for a moment that the only force is the gravitational force, so there's no air resistance. As the ball rises, the gravitational force does negative work to the ball, slowing it down to a stop, thus removing all of the kinetic energy from the ball. The ball then begins to drop back down. As it does, the gravitational force this time does positive work and returns all of the energy that it previously removed from the ball. Because the gravitational force returned all of the energy to the ball that it previously removed, we define the gravitational force as a conservative force. The second characteristic is that the work done by a conservative force is path independent. What we mean by path independent is that as an object moves from an initial location to a final location, the path that the object follows does not affect the amount of work that the conservative force does to the object. Only the initial and final locations will affect the amount of work that the force does. To explain this, I'll use the example of throwing a ball up into the air again. Say this is done repeatedly, that is to say the ball is thrown up and down several times. The gravitational force is then adding and removing the same amount of energy over and over, so that in the end, it doesn't matter that the ball was thrown up and down, say 20 times. The net amount of energy transferred to or from the ball by the gravitational force just depends on where the ball started and where it finished. In addition to the force of gravity being an example of a conservative force, elastic forces are another example, such as the force from a spring or rubber band. Elastic forces like these are only approximately conservative because they'll dissipate a bit of energy as, say, heat, so that it's not automatically returned back to the system. But they will usually be considered to be conservative forces in this course. In this course, the gravitational force and elastic forces are the only forces that will be considered to be conservative forces. Now let's discuss non-conservative forces. The characteristics of a non-conservative force are that when a non-conservative force does negative work and removes energy from a system, that energy is dissipated or transferred into a form that cannot be easily returned to the system. The classic example of a non-conservative force is friction, where the friction force might slow down an object by removing kinetic energy from the system and then convert that energy to heat. This heat or thermal energy might then be dissipated into the surrounding air, where it cannot be easily returned back to the system. A second characteristic of a non-conservative force is that the work done by a non-conservative force is path dependent, meaning that as an object moves from an initial location to a final location, the path that the object follows does affect the amount of work that a non-conservative force does to the object. Again, I'll use the force of friction as an example. Say you want to slide a book across a table from location A to B. If you slide it in a straight line, then the friction force removes energy from the book, primarily converting it to heat all along this straight path. If instead you slide the book in a meandering, longer path from A to B, then the friction force will remove energy all along this longer path, thus removing a greater amount of energy and dissipating a greater amount of heat. Friction is a common example of a non-conservative force, but there are very few conservative forces, so in this course, non-conservative forces can be considered all forces except the gravitational and elastic forces. So in addition to the friction force, tension, the normal force, a pushing force, a pulling force, etc., are all considered non-conservative forces. So now let's get back to potential energy. Because the work done by a conservative force is stored energy, we typically rename that work as a change in the potential energy of the system. Consider the example of throwing a ball up into the air again. As the ball rises, the gravitational force does negative work, slowing the ball down. And we can also recognize that positive energy is being stored in the system. So that means the mathematical relationship is this. The change in the gravitational potential energy of the system is equal to the negative of the work done by the gravitational force. Or we can write a similar equation for an elastic force such as the spring force, where the change in the potential energy of the system associated with the spring force is equal to the negative of the work done by the spring force. As we'll see, this renaming can be a very useful way to analyze energy associated with the conservative forces in the system. Also, we're making a subtle restructuring of the system when we do this. Up to this point, work has been associated with a force from an object that is external to the system. But now, when we discuss potential energy, we're going to define both objects involved in the system. For example, when we previously talked about a ball thrown up into the air, the ball and the earth will now be the system when we talk about potential energy. So for the equations I've written here, the change in the potential energy is a change in the potential energy of the system. And now let's see how this renaming impacts the work-energy theorem. As you should recall, the work-energy theorem states that a change in the kinetic energy of the system is equal to the net or total work done to the system. So now what we're going to do is split up this net work into work by conservative forces and non-conservative forces. And then we'll rename the work by these conservative forces to be the negative of the change in the potential energy of the system. The equation then becomes this. And if we continue to organize the equation so that the change in the system's energy is on the left side of the equation, then we can move this potential energy term to the left side of the equation as well, like this. So now we have modified the work-energy theorem to separate out the potential energy of the system. Even though at its core, this is the same equation as before, in this form, it's typically referred to as the conservation of energy equation, where delta KE is the change in the kinetic energy of the system, delta PE is the change in the potential energy of the system, which is associated with conservative forces, i.e. for our course, just the gravitational force and the elastic force. And then WNC is the net work done to the system by all of the non-conservative forces, or in other words, all of the forces other than the gravitational force and the elastic forces. As a matter of definition, I would also like to point out that the term mechanical energy refers to the combination of the kinetic energy and potential energies of the system, or the change in the mechanical energy of the system is equal to the change in the kinetic energy plus the change in the potential energies of the system. The last thing I would like to do in this video is to develop an equation for the potential energy associated with the gravitational force. We will also develop such an equation for an elastic force in a later video. For this derivation, let's start with the definition of the change in the potential energy, and then apply this equation to the gravitational force, so we change the subscripts to g. And now let's apply this equation to a ball that has been thrown up into the air. For this analysis, we'll assume the only force acting on the ball is the gravitational force, and we can consider the gravitational force to be constant when near the surface of the Earth. So that means we can use this equation for work, which is force times distance times cosine of the angle between them. Using the variables in the figure, we can then write it this way, and then recognize that the gravitational force is mg, and the cosine of 180 degrees is just -1. So then the equation becomes this, mg delta y. And so now this is the equation for the change in the gravitational potential energy. It's important to recognize when applying this equation that the y-coordinate is vertical, or in other words, it only refers to height. This means that the gravitational potential energy does not vary with horizontal displacement, but only with vertical displacement. Also notice that in this derivation, we use the gravitational force equation mg and assume that it was constant. This is typically only true when near the surface of a large celestial body like the Earth, so we should make note of that restriction as well. And then expanding on the derivation, we can also recognize that mathematically the deltas can be dropped, so we can also get an equation for the gravitational potential energy for a given value of y, or in other words, for a given height. So that's the end of the derivation, and it brings us to the end of the video on potential energy. In the next module, we'll learn to apply the conservation of energy to various situations that involve changes in gravitational potential energy.